the 6th episode of the Young Researchers Forum on Detonation. On schedule today, we were supposed to have Saeed Taleb. Unfortunately, he couldn't make it today, so taking his place is going to be your co-host, Dr. XiaoCheng Mi. He'll be presenting some of his doctoral work on the detonation propagation under the influence of spatially inhomogeneous energy release. XiaoCheng Mi received his PhD degree in mechanical engineering at McGill University in Canada in 2018 under the supervision of Professor Andrew Higgins. From August 2018 to February 2020, he was supported by the Canadian NSERC postdoc fellowship to pursue a postdoctoral appointment at the Centre for Scientific Computing in Cavendish Laboratory, University of Cambridge. He was directed by Professor Nicholas Nikoferis. Since March 2020, he has been a postdoctoral researcher at the Alternative Fuel Lab at McGill University in collaboration with Professor Jeffrey Bergthorsen. Dr. Mi's research interests include gaseous detonations, shock compression, and detonation of energetic materials and metal fuel combustion. We'll be recording this video. It's going to be edited, and then it's going to be published once the presenter accepts the final version. So if you have any questions, I invite you to type them in the chat so you don't forget them, and then we can address them at the end. And with that, I'd like to welcome Dr. XiaoCheng Mi.
Yeah, thank you very much, Jem, for your introduction. So my study is actually about the gas phase detonation propagation under the influence of a spatially inhomogeneous energy release. So why we do this study? What is the thought process for us to come up with such a problem? It's actually the following. So for gas phase detonation, we know that it can roughly be categorized into these two different types of detonations. One is weakly unstable, and the other is unstable, right? So why I say weakly unstable, because for multi-dimensional detonation wave, it's never planar. It's never like a stable wave dynamics, right? Like it always have this cellular structures, features of this transverse waves interacting with the leading shock front. And for weakly unstable detonations, you have this like a regular cell structure, or like this is like a numerical suit foil. Like this can also be obtained from experiments. So you see that this weakly unstable detonations leaves this regular shape detonation cell structures. And if you look at the wave structure, you see these self-repetitive patterns along the shock front, right? So if you have this kind of detonation wave, and if you perform a average analysis, that means you track the shock front and perform an averaging analysis for the flow field behind the shock, you see that this red dashed line is the average profile, is very close to that of a ZND structure. ZND is just a very simple detonation model, pictures the detonation in a 1D laminar-like structure, which has a leading shock front, and follow the shock front, you have a gradual energy release process, and this will accelerate the flow up to a sonic point, right? So if the average profile of a weakly unstable detonation is very close to the ZND's picture, that means although you have these multidimensional features or transverse waves, actually these instabilities, these multidimensional features are not that important, right? Like the dynamics can be pretty much explained by this one-dimensional planar or laminar-like detonation dynamics model, right? But what if the detonation is unstable, right? Like it is for unstable detonation, you always see this kind of cellular structure printed on the suit foil. You cannot like identify like one unique cell size. You have like larger cells, smaller cells, which are distributed non-uniformly on your suit foil. And if you look at the flow structure, you also see this front structure, front shock patterns are not periodic. They are not like repetitive, right? And for this kind of detonation, if you perform the same averaging analysis, you see that this red dashed line, the average profile significantly deviates from the ZND profile, which is the black line here. So you know that for such highly unstable detonation waves, the ZND model fails to describe the dynamics, right? So what we can, like if we want to learn about the detonation waves in this very highly unstable mode, we need to take a closer look into the experimental evidence. So these are some pictures obtained experimentally. This is the Schlieren graph, and on the right is superimposed the Schlieren graph and this laser luminous graph. And from this experimental evidence showing the detailed structure of methane oxygen detonation, we can see that the wave pattern and the flow field behind the shock wave is indeed very complex. And this features all this incident shock, triple point, Mach stems, and you can also see this large pocket which are undergoing very slow reaction. They are not like triggered. The combustion of this large pocket is not triggered by the shock compression, right? It undergoes like a much slower reaction process. So this is a picture that Professor Radulescu conjectured about the combustion processes behind a highly unstable detonation wave. And you can see that there are regions that are undergoing a very fast reaction triggered by strong shock compression, but there are also regions that undergoes slow combustion, which is controlled by diffusive or molecular transport processes. And also these processes are influenced by hydrodynamic instabilities. So for such a structure, that energy release is highly non-uniform in terms of the reaction rate, right? And it's what give a rise to this non-uniformity in reaction rate is actually a very non-uniform combustion mode, like the combustion mechanisms governing different regions or different amount of reactant is so different. So you have this highly non-uniform energy release field. So with this complex structure of energy release behind an unstable detonation wave, what is the fundamental propagation mechanism that supports such a wave to go forward? And you know, to answer this question, like if you know the answer of this question, you can understand how does unstable detonation respond to losses, right? Like how can it survive under different type of losses, right? And it's only you can answer this question. Let me turn on my pointer. So it's only after you can answer these questions, you can explain this trend that has been observed experimentally, that cellular instabilities can actually enhance the propagation ability of detonation waves, right? So I think, in my opinion, these are the most fundamental questions that we need to have an answer or have a better understanding to develop further applications or anything we go further from fundamentals. We need to build this strong foundation of our knowledge. But to do this, for sure, like we need to have like more experimental input. We need to have like better picture of the detailed structure, and from this structure, from this visualization, we should have like we need to have a quantitative measurement for different combustion processes or the reaction rate at different regions. But to get this to get this experimental input, it's not that easy, right? Like I know there are some ongoing efforts, but it still is not as mature as it's just not get to the level that we can get the useful information yet. So I would talk about like how we can approach this problem by doing numerical simulations. And if we want to use numerical simulations to get valid result or make to perform some physically sensible studies, we need to be very careful with the numerical methodologies we use, right? Here, I'm not going to talk about a lot of detailed algorithms, but just the idea or the somehow the philosophy or the overall strategy to model unstable or gas phase detonations, like how how should we examine the methodologies we use, right? So we know that actually for regular or weakly unstable mixtures, it's not that hard to resolve because as I said before, the overall structure or the overall dynamics is not that different from the ZND model, right? Like all this multi-dimensional instabilities, whether you're resolving it right or not, actually it doesn't matter that much, right? So these are actually, I would say, relatively easy case, right? But for this type of detonations, what we need to develop is actually some even simpler or even cleverer models than just performing the high fidelity CFD simulations, right? Maybe something based on ZND model or some reduced order modeling that we can use to approach this problem in an even simpler way, right? But what we need to be careful with is how we model unstable detonations, right? So Brian Maxwell, he in his PhD he demonstrated of using subgrid reaction and turbulent combustion models to model unstable detonations, and he can demonstrate that using this kind of a model, he can achieve numerical convergence, right? But for this kind of model, if you want to make it work correctly, you need to calibrate this subgrid reaction models. Maybe like there are different opinions, like whether this is calibration or you can somehow get some fundamental input to come up with the parameters you use in the subgrid model. But somehow like you need some tuning, you need some, like you need to tune the parameters or the model against some experimental result to get the model give you right answer. So I think this is very good approach for engineering purposes, but we need to be very careful when we use this for fundamental studies, because you are actually tuning the system to match some experimental result. It's not like a naturally evolved fundamental study, right? So here, like I think, like perhaps the most reasonable approach to do fundamental studies with numerical simulations is using DNS, direct numerical simulations, without any calibrated subgrid models. But like this is actually very hard. I think most of you know this paper shows like this is a notoriously hard problem to resolve. Like these authors actually increased the resolution up to 1,000 computational cells per half reaction zone length. You can see the flow features, the wave structure and the flow field features are still changing, right? So it's not that hard to, it's not that easy to achieve numerical convergence by doing DNS of of an unstable gas phase detonation. And the other thing is like there is no rigorous test on the validity of the numerically captured diffusive, diffusion, diffusive processes. So I will come back to this point later in my talk. So as I show all this evidence or this previous works, what the point I'm trying to make is it's actually not that easy to use computational modeling to capture the essential physics or the combustion nature of detonation wave, right? There are a lot of uncertainties, and it's like this approach might not seem that might not be like that mature as it seems to be, right? Like there's a lot of holes or a lot of traps you need to be careful with, right? So in my PhD, actually, instead of exhausting the computational effort to resolve this very hard to resolve combustion modes of the unstable detonations, we actually try to attack the problem from a different angle. So how about like we don't capture any of these complex combustion natures of an unstable detonation? Let's just try to impose some inhomogeneities in energy release, and then we see how does this imposed or artificial inhomogeneities of energy release influence the detonation propagation behavior, right? And we know that we cannot use this simple ZND model to explain what is going on for an unstable detonation. But how about we do this? Let's collect all the reactant or the reactive material and concentrate them into this discrete, this spatially discrete reactive sources. And then we let these sources to induce a synthetic wave structure. And this synthetic wave structure has this non-uniformity in energy release. And this is somehow similar or maybe capture some essential features of the non-uniform reaction field field in an unstable detonation, right? And by doing this kind of by following this approach, we studied two systems of numerical experiments. The first one is we impose or introduce these reactive discrete sources to an adiabatic system, and with this system we can see like how this discrete sources influence the propagation speed of detonation. And in the other system of experiments, we introduce these discrete sources into a system with losses, and we see how does the inhomogeneities of energy release influence the propagation limit of a detonation wave. So I will first talk about this system. Like for a homogeneous mixture, like this is the classic Chapman-Jouguet theory, right? Like you just for a homogeneous mixture, if the reaction stops or the overall mixture reaches an equilibrium state at the sonic point, you can get this. You can solve your conservation equations to get your CJ detonation velocity, right? And this is the classic CJ theory, assuming only a homogeneous mixture of the reactant. And what we do, we can just have this simple case of creating this inhomogeneous system by collecting the reactant into these layers of discrete sources, right? Like they are separated by inert gaps, right? And in these layers, I set this reaction progress variable to be 1. This reaction progress variable is, you can consider it as a normalized concentration of reactant. So if Z equals to 1, that means that in the layer it is reactive. And if it is 0 in the gap, that means that the region in between is inert, right? and the spacing between each two layers is L, and the width of each layer is W. So you can calculate this one-dimensional spatial discreteness, which is denoted as gamma, right? And if gamma equals to 1, that means everything is homogeneous, right? Like it's the same scenario as the classic CJ theory considers. And if you're going to the limit of gamma equals to 0, that means the layer becomes a discrete point source, right? And the energy release within by each discrete layer is actually modified, you know, like by gamma, right? Like if you have a gamma smaller than 1, then the energy release within the layer is increased proportionally, so that the overall energy can be maintained as Q, right? So the average energy density of the system is always maintained as Q, as you change your discreteness parameter or your source spacing, right? So the system can be initiated by a high pressure region, and if you let the wave propagate for a certain for long enough distance, you can get an average velocity. So the question is, how does these two velocity compare to each other, right? You are controlling the Q is the same. You are just discretizing the spatial distribution of energy release, right? So this is just like a brief description of the Garmin equations. It's based on the reactive Euler equations, right? What I want to draw your attention to is the formulation for the specific total energy. So you have the discrete parameter, discreteness parameter gamma here, and you have this Z is the normalized concentration of the reactant. So by doing this kind of discretization, you're actually we are keeping density, pressure, and temperature uniform everywhere. So the only thing changes is the energy release by the reactive material, right? So these are some sample results, and on top, this is for like 1D simulations with the layers, and in the middle is the 2D simulations, also with discrete layers, and on the bottom is 2D simulation with this regularly spaced squares of discrete sources. And you see that if you keep the spacing between the sources constant and changing this discreteness parameter, and you see that when this discrete parameter equals to 1, the detonation velocity equals to the CJ velocity. So on the y-axis is the average propagation velocity in the discrete system divided by the corresponding CJ velocity, right? So at this limit, it recovers the CJ velocity. And if you go to very small gamma, that means like in the limit of gamma going to 0 is in the limit of point sources, you see that the velocity of the average wave propagation becomes significantly greater than the CJ velocity, right? And you see the similar trend if you fix your gamma and change the source spacing. And if the source spacing is very small, it's like close to the reaction zone thickness, then the resulting wave propagation velocity is very close to CJ velocity. And if your source spacing is very large, it becomes like 10 times or 100 times of the reaction zone length, then you see that the average velocity increases also to a value that is significantly higher than the CJ velocity, right? So we want to understand why this is the case, right? We need to rationalize this super CJ wave propagation. And what I did, or we thought like this averaging analysis can help us to bring this complex problem into a framework that we can understand as a ZND wave or 1D laminar-like detonation structure. So we perform this spatial temporal averaging. So we can get a averaged profile for density, pressure, and reaction progress variable, and so on. And this here, what I plotted is a case that you have a significantly discreteness. So the propagation speed is much greater than Cj velocity. And if you plot the average pressure profile, you see that when the flow reaches the average sonic point, the average pressure is actually much higher than that of the Cj pressure, right? So what does this mean? Like if you plot this average profile on a PV plane, like for the homogeneous case, you see this is the classic Cj detonation, or the ZND structure of detonation. When it reaches this sonic point, when it reaches the sonic point, it actually reaches equilibrium, right? Like this is the Cj solution, and you see that this Cj solution, or the propagation speed, is the the relay line associated with this Cj speed is tangent to the Hugoniot of the equilibrium equilibrium state with a complete energy release, right? But if at this significantly super Cj conditions, you see that the velocity basically is higher than the Cj velocity. So this is known as the weak detonation solution, right? And if you perform this kind of analysis, and you can measure the fluctuations at this average sonic point, you see that these fluctuations are still significant around this point. So that means at this average sonic point, the flow is not at its equilibrium state, it's non-equilibrium, right? And this super Cj wave propagation can be understood as a weak detonation with a non-equilibrium state as at this effective or average the sonic point. So what more we can learn about this detonation, super detonation, super Cj detonation velocity, or this detonation propagation over like a highly discretized reactive medium? We can think about like what happens at this limit when the discreteness parameter goes to 0. Right, this is the asymptotic limit that the wave propagation actually becomes a sequence of blast waves triggered by the previous one, right? So this is actually the XT diagram showing the pressure contour from the 1D simulations with the discrete layers, and you can see these are the energy release of discrete sources. And this, in this case, we actually make the gamma very, very small, so it almost becomes a point source, right? Like it's actually triggered upon the arrival of the previous blast wave. And once it's triggered, it releases energy. It generates 2 blast waves going backward and forward. And the forward blast wave will trigger the next discrete source and keep going in this way, right? So if we are in this limit, then we can actually do another test. We can say like, okay, if this is very small, then we can ignore the detailed reaction mechanism, or we can say like we just ignore any realistic chemistry or the realistic energy release processes. We just use this very simple energy deposition model that like if the source, this is supposed to be a source, and once it's compressed or triggered by a previous blast wave, after a certain delay time, you just deposit energy directly as by increasing the pressure of this source, right? So this is it doesn't represent any real chemistry or any real combustion process. It's just a very simple way to deposit energy to the system. And if you do this, you can see that actually the result, these circles are the result from this simple instantaneous heat release model. They actually agree very well with the result you get from Arrhenius kinetics at this highly discretized limit. Right, for very small gamma, again, this is the limit going to point sources. Right, you see this super CJ velocity is only dependent of gamma, which is the ratio of your specific heat, and it just doesn't really depend on the detailed mechanisms of energy release, right? So if that's the case, we can maybe come up with a simpler model instead of doing CFD, solving Euler equations. Maybe we can come up with an even simpler model for this phenomena. So one attempt we made is actually using this Burger's equation, the analog model. So basically, you just have like this one single equation that tracks this rho, but this rho is not really density. It's just some flow, some quantities associated with your flow, right? And like this has been first developed by Maida and also Fick and Davis to use this simple equation to capture some essential features of detonation wave. And I just use a similar model, but for the reaction or the energy release, I try to mimic this instantaneous energy release after a delay time that I showed in the previous slides for Euler equation simulations, right? And if we use this simple model and we make the point, the sources of energy as the point sources, we can actually find an analytical solution, and we can construct this sequence of waves by just constructing by superimposing all these analytical solutions, right? So this is just a demonstration of how this energy release is implemented, right? And if you triggered this is a wave front from the previously triggered source, and once it passes across a new source, after a certain delay time, the new source will start to deposit its energy, right? Like you just add this triangle onto the wave profile, and this wave will propagate forward and eventually merge into with the leading shock front, right? But like if we examine the average velocity for many different cases with randomly distributed sources, we see that if you run the simulation long enough, the average velocity always goes back to CJ, right? You don't see this super CJ phenomena. So unfortunately, this nice and this nice analog model that you can solve all the wave dynamics by with analytic solutions, it just cannot capture the super CJ propagation, right? So then we think about like how can we actually build a toy model, right? Just based on the Taylor-Sedov point source blast wave solutions, and we just build different parts of this model by making different assumptions to see if we can somehow or qualitatively capture this sequence of point source blast waves solution. So the Taylor-Sedov point source blast wave solution, it looks like this. And if you have this wave, like this energy release generating two waves, one going forward, one going backward, you have this partition of the source energy, right? Only half of the energy of the source going forward, right? But this is under the consideration that the source is triggered in a uniform medium, right? But in this case, since the the source, you consider the source is triggered right up on the front of a blast wave. So that means like it's releasing its energy to both directions, but both the medium or the flow properties on each side of the shock wave is different, right? So the energy partition is not half-half, right? So you need to actually consider how this point source partitioned into forward-going blast wave, you can find in my PhD thesis this you can actually find an analytical solution for how energy is partitioned into the forward and backward going blast waves, knowing all the states across these shock waves, right? And you can see actually this partition is only depending on gamma. It doesn't depend on other parameters. But this is also in the, assuming that this is a very high Mach number, right? So this you can analytically solve this partition parameter. And the other element you need to put into this toy model is the previous source must have some carried over energy into the next blast source, right? But this is not that easy to come up with an analytical solution or a closed form or something that you can get from first principles, right? So like an assumption we made is the kinetic energy possessed by the piston motion of the flow driven by the previous or the flow that drives the previous blast wave will be carried over to the new point sources, right? So you actually have another addition term in the point source blast, which is carried over from the previous source. So by having all these considerations or all these assumptions, you can calculate the instantaneous wave speed, and you can normalize that with respect to the CJ velocity. You see these black lines are those we get from, are the velocity we get from the simulations, and this dashed line is obtained from this toy model. And you see that qualitatively it follows the same periodic behavior, right? Like from source to source. And but the thing is like this this toy model over predicts the velocity for a large part, right? So if you plot this this average velocity with respect to the CJ velocity, you see that this follows the same trend as a function of gamma, right? But it is still like significantly greater than these simulation results. So this is not like a very rigorous, mathematically it's not a rigorous model, which is you know, by constructing different assumptions or different simplifications, we just put everything together to be this heuristic model. But I think there is something essential is captured there, like, you know, like it just in this limit, you just have a sequence of point source blast waves, you know, give you this propagation speed, right? So yeah, here I will try to summarize what we found from this adiabatic system of, you know, for this adiabatic system, like what we see, like how these discrete sources influence the propagation speed of the detonation wave. So for like very highly discretized energy sources, the detonation speed is actually significantly faster than the classic CJ solution, assuming a homogeneous reactive medium. And this super CJ wave propagation can be understood as an averaged or like, you know, like this averaged detonation profile of this super CJ wave can be understood as a weak detonation, right? This weak detonation is due to the non-equilibrium state at the average or the effective sonic plane. And in the limit of very highly discretized sources, the wave propagation asymptotically approaches sequentially triggered point source blast waves. Is that what we try to model using this toy model, right? And this, I have some more speculations where there are like some more unsolved or unanswered questions. So, like, what is the implication of this super CJ wave propagation? I just don't know. I think it might represent some kind of upper limit of how fast a reaction wave can propagate, like being supported by the same amount of energy release. Right, and can we actually get an explanation for this super detonation, super CJ detonation speed from fundamental thermodynamics? Like if we can consider entropy or something even more fundamental than this weak detonation solution, right? Like I just think like this, what we found so far is more like describing the phenomena, but I still don't know the answer, like what is the more fundamental reason give a rise to this super CJ propagation speed, right? And also, like as I said, like before, what I showed is a toy model. Is there a way to mathematically more rigorously obtain a closed form analytic solution for this speed? And also, this is another implication. Perhaps all unstable detonations are weak detonations. Right? It's just like the deviation from CJ speed might be too small to be experimentally detected. Right? Yeah, I think I will stop here. Like if there's a comment or question regarding the first part, and then I will continue with the second part on the propagation limit.
Thank you, XiaoCheng. We have a question from Jorge Diaz. I don't know if, Jorge, do you want to ask it yourself?
Hello, can you hear me?
Yeah, I can hear you, yeah.
Great, yeah, I think it was in slide 7, I think was a comment. You were describing this this inhomogeneities in the system. This is space inhomogeneities.
Right.
However, all the different layers are separated in a very uniform way.
Right.
I mean, they are all the same distance from one another.
Yeah.
And I naively thought, I'm not an expert in the field, that's why I'm asking. I naively thought that when you were referring to this especially inhomogeneous system, that these layers will be distributed in some sort of random or completely unpredictable way, that they will not be at the same separation. For example, L will change from one to the other. Is there a reason you keep this distance fixed, or what would happen if you make it different?
Right. Actually, for this, I just this is kind of like control study. I just want to make the discretization or the introducing the inhomogeneity in the most controllable way. So I start like this is like a very first scenarios I considered is in this regular or this fixed spacing way. So actually more studies I'm going to show later actually for the propagation limit studies. Actually, I keep the average or the mean spacing fixed, but in the medium or like especially in 2D medium, you have these square sources. You randomly distribute them, right? So for those cases, we still get the super CJ if we keep the system without any losses. Just keep a adiabatic system without any losses and examine the propagation speed is still super CJ with randomly distributed sources. Yeah, but for this 1D, just easier for analysis and like it's a more controlled study.
Yeah, and if I could, I have another question for what you did later. Even though you showed that it was not useful when you were showing this first toy model.
Right.
cannot remember which
yeah,
slide was.
the Berger's equation model.
Here, exactly.
Yeah.
So you said that you were even, so you did not use it, you find it didn't let the results that you wanted. But
Right.
in any case, I had a question here,
Right.
because you have in this equation, you have this dz to dt, and you're using the step function for z, because you want either the
Right.
either on or off.
Right.
And you said that you were able to solve this analytically, but the derivative of this step function will give you a collection of Dirac deltas. So you were, even in that case, that led to an analytical solution.
Right. I mean, analytically, there is this small, like a numerical or this tolerance or something you need to assume is like once you inject this triangle, like as you said, like rigorously mathematically, it should be like a direct delta function. But what I do is just like make it like very narrow, but like still has a finite width, so it's not mathematically that rigorous. But with this, we just make it smaller and smaller. We see that the overall propagation speed converges. Then we know that this. So there is as you see, there is still a parameter that we need to do numerical convergence on, right? So it's not exactly the delta function, right?
Great.
Yeah.
Great. Thank you.
Yeah. Thank you for your question.
And we also have a question from Cesar on slide 12. Cesar, do you want to ask it?
Yeah.
Oh, yeah. I have a question about the Sedov-Taylor model that you use, XiaoCheng. The length scale here is external to the model, right? I mean, if you want to compute the average velocity of the propagation, at the end, you need to give some extra information before using that, because there is no length scale for the Sedov-Taylor, right?
Oh, well, like in this case, actually, what I did is like this. Like actually, for the length scale, actually, I average the length scale by the spacing, because here I assume that is equally spaced. So basically, like this L is 1, right? Like I average this by 1, and this scale is like if I collect energy within this region and concentrate that to one single point source, and this is actually my Q, right?
Yeah.
So in this case, actually, you see like this. It's a bit hard to explain like this, but if you have this Q is the collection or the total amount of energy released across this unit length.
Yes.
So everything is non-dimensionalized with respect to the average. To the source spacing. Right.
So then, if you want to use this Sedov-Taylor model to predict the velocity, then you have to provide this length from the previous picture or somewhat. It cannot be written in terms of the induction length or something that you can predict before the detonation evolves. Something like a characteristic of the reactive mixture.
Right here, well, we can, but I didn't do it that way because this is actually in the limit that like the source just becomes the point source and the instantaneous reaction. So for this analysis itself, it doesn't really have a characteristic reaction length, right? Because like if you have the same Q, you have the same gamma, by having different reaction model, like different EAs, whether the first step or two step, you can have different characteristic reaction length. But since here we are assuming at this, actually that's what we found like from the previous simulation results. If we are in this limit of the sources are all like in the limit of point sources, the reaction model, the detailed reaction process doesn't matter anymore. Right, so that's motivates us to actually consider this kind of like simplified model, considering point sources. So actually, this in that sense, then we don't really have a characteristic reaction zone length for this analysis, right? Is yeah, but like if you want to map this back to the CFD simulation for Euler equations with some, for example, single step Arrhenius model, we can do this mapping. You can convert that into into how much, like for example, through the length scale of the source spacing, you can map this back to a realistic system which has a reaction zone length, right?
Okay.
I don't know if this is clear.
Yeah. I got it.
Okay.
Thank you very much.
Yeah, thank you.
Perfect.
Thank you for the question. Thank you.
And we have another question from Mark Short.
Yeah, sure. Yeah, Mark, maybe he's
Hey.
oh, hi, Mark.
Yeah.
Yeah, I can hear you this time. Yeah.
Figured it out this time.
Yeah. Okay.
So,
Thank you.
quick question on what it effectively means to be an average sonic point. So what I take you're doing is actually you're averaging the flow field, and then you're calculating the average sonic point relative to the average field. You're not essentially taking instantaneous sonic points and then averaging those, I assume. So the question really is that in unsteady flow, which essentially is what you're averaging, a sonic point is really only instantaneous relative to the instantaneous location of the shock point. So at any point further in time, characteristics can happily pass through that state. And essentially, they don't really have the same meaning they do in steady flow, where essentially a sonic plane actually represents a barrier of information coming from the region behind to the region in front. So what does it effectively mean to be talking about an average sonic point in the context of your theories then?
Right. Actually, this is actually somehow like related to another study I did like after my PhD. Actually, I agree. Like this, the sonic point or average the sonic point may not be the most meaningful terminology to describe this phenomena. It's actually what I think, in my opinion, is actually more like if you do this statistical analysis, you have a statistical or probability distribution of your characteristic speeds, right? Like across this whole detonation reaction zone region, and this average point or average sonic point, or the location of this average, the profile across this, for example, this U plus C in the reference frame of the shock equals to 0. This is only when the beyond this point, like the characteristics originating downstream are very unlikely to reach the shock front. So it's all on a probability or a statistical sense, right? I mean, you can always even like you go like very, very far downstream from the sonic point. There's also a chance that maybe one characteristic you can somehow propagate and transfer information from downstream to the detonation front. There's no sharp barrier for this unsteady system. There's no such a sharp barrier for information to be totally impossible to be transferred to the shock. But beyond a certain point, the probability drops to be very low. So I think that's the sense of this average sonic point. And the more, I think that the more reasonable or the more meaningful terminology should be related to the statistical property or the probability of having a supersonic or subsonic flow with respect to the shock front. Yeah, I think that's just my explanation. I don't know.
Yeah, I mean, there's some definite. I mean, it comes down, I think, to the different ways that one can essentially think about averaging these highly unsteady flow states, whether it's Lagrangian, Eulian, instantaneous, as you've done a homogeneous averaging. So thinking in terms of probability functions is probably a good strategy for doing so. So no, that sounds great. Thank you.
Okay, thank you, Mark, for your question. Any other questions or comments?
Oh, we have a comment from Matej Redleska.
Yeah, please go ahead, Matej.
Hi, XiaoCheng. So it's a comment in regards to the strategy that you use to explain why you have this this super detonation phenomenon. If you study things in the limit of very strong shocks, and you get Taylor-Sedov blast waves, they're extremely nonlinear and very difficult to work with.
Right.
But if you study the other extreme of like very weak shocks, then it's extremely easy. So you could repeat your work in the limit of a weak heat release, and then you see just acoustic waves bouncing forward and bouncing backwards, following each reaction, and then you would see like what's the strength of the wave going back and what's the strength of the wave going forward, and you'd be able to unravel this mystery much more easily, I think.
Okay. Yeah. Thank you. This is actually very interesting. Very interesting direction. Yeah. Like I agree. Like this you know, like this sequence of point sources is really hard to have an analytical way to solve everything because it's so non-linear. And yeah, I would like to consider this acoustic wave, but I just don't know like if we can still put everything back to this kind of average ZND paradigm, because I don't know, just this propagation mode, can we reconcile that with this you know, sonic plane and how energy release accelerate the flow towards sonic plane and have this information barrier and so on. This I don't know, like with acoustic waves, whether, you know, things can be reconciled on this point, but it's interesting. I would, you know, I would like to consider this. Yeah. Thank you for the comment.
Welcome.
Yeah. Like the other is actually, I would, you know, consider like to reintroduce these discrete sources to a system that you the detonation experiences losses, and to see how does the inhomogeneities in energy release influence the propagation limit, right? And this system is actually a it has been studied by a number of researchers over the past few years. I think actually our designated speaker today is Saeed Taylab. He's really the expert, perhaps one of the most active researcher on this problem over the past few years. So I will talk about like my version of this study. So basically the system is like you have a detonatable mixture or reactive layer of gas, and this layer is confined by an inert layer of gas, right? The gas, this is a compressible, and we call this the yielding confinement. So once the detonation wave comes here, then behind the leading shock, the detonation wave the flow behind the leading shock expand laterally. So the detonation wave will experience losses in momentum and mass in the lateral direction. So the gas expansion is not only supporting the wave to go along the propagation direction, but you have this lateral motion that also takes the energy released by the chemical reaction, right? So in such a scenario, that you can always characterize the amount of losses experienced by the detonation wave by the thickness of the reactive layer, right? And if you decrease this reactive layer thickness, you are expected to see a larger velocity deficit from the CJ velocity. And if the thickness is below some critical value, the detonation just fails to propagate. So my implementation is just to introduce this randomly distributed energy sources into the reactive layer, and to see how this inhomogeneity in energy release influence the propagation limit, or the critical thickness of the reactive layer, right? So again, the discreteness of the reactive source are again defined in this way, and inside each reactive source, the energy release is modified by the same ratio. So the overall energy release is maintained constant as the homogeneous case. So here are some sample results, sample animations. So on on top is the homogeneous case, and on the bottom is the case with randomly distributed inhomogeneous reactive sources. And I will play them here. So once it reaches the end, they just keep propagating forward, and I just switch the frame so that you know, for the simulation I can use like a relatively small computational domain to capture the dynamics. You see, at this relatively large thickness, h equals to 80. 80 is this length scale is non-dimensionalized with respect to the half reaction zone length of the ZND detonation. So this is h equals to 80 means the height of this reactive layer is 80 times the ZND half reaction zone length. So at this relatively large thickness, you see for both cases, the detonation can keep propagating. And if you reduce h to a thinner reactive layer and down to this h equals to 50, you see that for homogeneous case, the detonation wave actually fails to propagate. Right? You see the reaction just stops, and the strength of the leading shock wave just decays. But for the same thickness, if you have this randomly distributed sources, the detonation wave can keep going at the same thickness of the reactive layer. Right. So if we can summarize this result in this plot of average velocity versus Cj divided by Cj, and as a function of the inverse thickness of the reactive layer. So that means like in this limit, when this 1 over h goes to 0, that means it's an infinitely thick layer, which is similar to the ideal case or adiabatic system without any losses. And in this larger, if your 1 over h goes to a larger value, that means the thickness of the reactive layer is smaller and smaller, right? For this blue dots here, I plotted for the case with gamma equals to 1, which is the homogeneous case, right? You see that at this ideal case, the velocity just recovers the Cj velocity. And if you make the thickness smaller and smaller, it's just experiencing larger and larger detonation velocity deficit. And at some point, the velocity just dropped to very low value, or you can see that the detonation wave fails to propagate. So from this, you can determine a critical thickness for the propagation to keep going, right? This h star is the critical thickness. So if you start to make the reactive source discrete, we decrease the gamma to 0.25, you see that at this adiabatic case or the ideal case, the velocity goes up, goes to higher than the Cj velocity. I think this answers Dr. Diaz's question previously. So you have a random distribution of sources, and for the ideal case, it still gives you super Cj detonation. And you can see that as you decrease the thickness of the reactive layer, you also see a larger and a larger velocity deficit, but the velocity are greater than that from the homogeneous case for the same thickness. And this critical value of reactive layer thickness is smaller than that resulting from the homogeneous case. right? That means that the discreteness or the discrete sources actually extend the propagation limit of the detonation wave, right? So if you make it even more discrete, you can see this curve is further extended that way, right? And if you plot for this relatively low EA, this critical thickness as a function of discreteness parameter, you see that as you go from homogeneous, which where gamma equals to 1, to a very highly discretized sources, you see this decrease in critical reactive layer thickness. And if you go to an even higher activation energy, you see this change or this decrease is more dramatic, right? This, you can see this is significant enhancing effect by the discretized sources on the propagation limit for this scenario. Yeah, so let's try to look at what is going on for the homogeneous case and what is going on for this highly discretized case. So this curve, this 3 square point on top is for the homogeneous case. This is the critical thickness as a function of EA. So you see that as EA increases, this H, this critical thickness also increases. That means the larger EA you go, the harder the detonation wave to propagate. And this is actually contradicting the most of the experimental evidence showing that cellular instabilities or this sensitivity of the detonable mixture enhances the propagation limit or enhances the propagation ability of the detonation wave. So this has been actually noted, and Professor Radulescu has this paper published in 2018 stating this kind of a paradoxical nature between simulations using Euler equations and the evidence found in experiments, right? So this actually contradicts the experimentally found trend of sensitivity, the trend between the detonation propagation limit and the sensitivity of the detonable mixture. But you see that this dependence for inhomogeneous case or the case with highly discretized sources is actually the same trend, but the dependence is weaker, right? Like this increase is not as dramatic as for the homogeneous case. And if you go for larger EA, you see these curves start to become shallower, or like it looks like it's gonna become a plateau or even go the other way. But unfortunately, I didn't like go for like even larger EAs, because for even higher activation energies, to get the numerical converged result for these highly discretized sources becomes more difficult. And if I have time, or like in the future, is also a very interesting direction to see like what's gonna happen, like if I keep increasing EA, like how this curve gonna look like, whether it's going to curve down or just remains at the plateau. At this point, this is unknown. I don't know the answer for that. So we try to use this ZND model, like this model based on the ZND structure, without considering all the cellular structures or instabilities. And this is basically the Wood and Kirkwood model that can predict, or somehow like you get an estimation of detonation velocity as a function of the detonation front curvature. Right? This is so-called the dn-kappa relation. And then once we have this relation, we can use this Airing's wave construction methodology to construct a wave front. And by applying the sonic condition for the oblique shock at the end, you can determine the thickness of the layer as a function of detonation velocity. right? Like you can find the relation between your thickness and the detonation velocity, and also from this relation you can obtain a relation between the EA, the activation energy, and the critical thickness of the layer. So I won't go through the mathematical details about how to do this analysis. So basically, like by doing this, by constructing, connecting different pieces of models together, we can get this relation based on the simple one-dimensional Z and D or quasi one-dimensional Z and D model. And if we plot this curve, what happens is like this this curve actually agrees pretty well with the the case from the inhomogeneous discrete sources, right? For this relatively low EA, these two curves almost coincide each other, right? Like this remember these circles are not based on homogeneous mixture, right? But it well agrees with the Z and D based model, right? And it's only at this relatively large activation energies these two curves start to deviate. So like my explanation for this is because we have these highly discrete sources, and these sources force the energy to be released in the vicinity behind the leading shock. And this somehow, this picture somehow agrees better with the ZND structure or ZND model. Like all the reaction is triggered by shock compression, right? And for cellular detonations, for as you see from the animation I showed before, for this homogeneous case, you actually see this large unburned pocket detached from the shock front. Or from the experimental evidence, we know there are this slow reaction or slow combustion mode, and those cannot be captured by the ZND model. That's why these two curve, the homogeneous reaction simulation results deviates from the ZND prediction, right? And this is my speculation. I think maybe this agreement between these two explains why it is a smooth curvature or ZND based reaction model, or like the DSD theory or DSD model used for high explosives works relatively well, is because in condensed phase explosives, because of the sensitizing effect or the hotspot effect, the energy release is actually forced to be within the vicinity of the leading shock front, so that the overall combustion process is triggered by the arrival of the shock, right? By the shock compression. And but for cellular gas phase detonation, this is not the case. You have this large pocket which is governed by a different type of combustion mode, different from shock compression, right? And now, like, let's come back to this fundamental question I try to post at the beginning. I think this is a long-lasting problem for the fundamental research community of gas phase detonation. It's just like, how this unstable detonation propagate, and what exactly is the combustion mode or the wave dynamics that that is essential for this propagation, so it will respond to losses in such a way, right? Like this trend we try to understand or try to explain is cellular instabilities enhance the propagation ability of detonation wave. I don't know if my result can actually, give an explanation to that, because as I said, like, we don't know like what happens like if we go like for larger or more unstable case, how this curve will look like. If this curve will start to curve down, then maybe this whole methodology that we proposed using this energetic sources to mimic this non-uniform energy release is a good approach. We can actually capture some essential physics of how cellular instabilities enhance detonation propagation. but this still remains an open question. I don't think I get there yet. We need to look further into this. So I think like the question is like, you know, like I think since Professor Radlasco and his group are here, and I would like to consider or maybe ask for their opinions, like what we think like is the fast combustion triggered by this triple point or this explosion kernels, or this slow combustion maybe governed by diffusive processes are the most important mechanisms for this enhancing effect, right? Because we want to explain this enhancing effect of the instabilities, but the instabilities means not only the later, you know, the downstream slow combustion, but also this shock, you know, shock focusing, all these triple point interactions. Those also renders the reaction rates go very non-uniform, and you can give like you very high reaction rate locally, right? So which of these two different type of combustion is the most essential mechanism give a rise to this enhancing effect? So I think like maybe this perhaps is not a question for some of you. You think like there are already enough evidence showing that this inviscid model or the model or simulations based on inviscid Euler equations fails to capture the enhancing effect. And as I show here, I also failed as well, as all of us do. It gives opposite trend, right? Like you go higher EA, the detonation becomes harder to propagate. But my question is like this failure of the inviscid model, is it like, are we actually failing to model fast reaction or the slow reaction, or fast shock compressed combustion, or the slow turbulent driven or diffusive process driven combustion? This actually is not, you think maybe this is clear, you know, I think maybe Professor Radlasco's answer is for sure that we are failing to capture slow combustion. But if you think about this, this is actually some unpublished result. Maybe this also addresses Mark's question earlier. So this is statistical analysis of the wave dynamics that I, you know, used my code to solve Navier-Stokes equations, which you have this diffusive processes considered, and I just impose two constant Reynolds number, right? Like for these two systems, I just have very different Reynolds numbers, and I impose the constant Reynolds numbers, so that, you know, the viscosity, all these transport properties are not depending on temperature, but they just have this fixed Reynolds number to follow. So basically, I think this Reynolds number equals to 10,000 is about relevant to most of the detonation based on estimations. And this, I make the Reynolds number 1 order of magnitude smaller, which means that the flow is 10 times more viscous or 10 times more dissipative than reality. So if you look at this probability density distribution of the U plus C characteristics, you don't see much difference from this distribution, right? Like you see that I try to mark this averaged sonic point, right? So this average, as I said, it makes sense in terms of probability, but you can still use that use it as an indication of how the flow structure or the overall wave dynamics is results from the simulations. And you see that it doesn't change that much. The difference is very minimal. And this is the statistical analysis I did over like a large amount of a snapshot of you know, simulation data for the flow field data. So that means like the simulation we are actually doing with NS equations, even there are many other papers published now, they are considering during more realistic diffusive processes, we are actually not resolving the physical diffusive processes. The numerical diffusion perhaps still dominates. That means like when we are actually resolving Euler equations, or we are resolving NS equations with different diffusivities, we are actually all resolving numerical diffusion phenomena. And if that's the case, that means that numerical diffusion is greater in your inviscid simulations, right? Because they just don't make any difference. Like you just your numerical diffusion is much greater than the physical diffusion you want to build into your model. And if that's the case, then we should see that the inviscid simulations give us the opposite trend, right? If the hypothesis is this slow combustions are important. If we are missing slow combustions, or we don't have these slow combustions being resolved in the like the slow combustions are not that effective in our simulations, then we see this kind of like a wrong trend. But that's not the case if your numerical diffusion is actually more dominant, right? So if the numerical diffusion is more dominant, we should see the opposite way. But we're still seeing the inviscid simulations giving this contradicting trend. My explanation is perhaps the fast combustion is not resolved properly. It's, you see, like most of these people just say, oh, we use Vino, we use other fifth order, sixth order accuracy scheme. But at the shock, or especially all this triple point, all this complex, strong shock interactions, you are just at the first order accuracy. And perhaps it's just we are not resolving the strong reactions, strong kernel of explosions properly. That's why it gives us the a poor propagation ability of more sensitive detonable mixtures. And that's just my my hypothesis. I don't know if that's correct or not, but I think like we should do this very rigorous numerical convergence or statistical numerical convergence studies to actually know like whether we don't just like put all the physics, put all the transport phenomena linked, put all this chemical generated transport properties into NS equations and hope that just give us the right diffusive physics. That's just at least before rigorous testing, we shouldn't be that sure about that, right? And that's just my opinion about that. And every time I look at this fundamental question, I feel my PhD is come like this. I was attempting to tackle this problem, but I don't know if I succeed. I think the contribution I made is perhaps very little, but still maybe incremental, but not that significant. And I hope like we can all together shoot more bullets to this balloon and shoot them harder. And I would like to thank you all for your attention, and we can further discuss this. Thank you.
Thank you very much, XiaoCheng. Are there any questions or comments? While people think of their comments or questions, I guess I'd ask you, I think the slow combustion is the one that we're not capturing right. And if it comes for the fast combustion, how would you see that being the problem? So I've done some viscous simulations of triple point reflections, and although there is differences between the viscous and inviscid temperatures and pressures, they're not that big. And where you do see a big difference is, they along that shear surface of the that you see in the triple point reflections. And that's where, that's where I'm thinking, or I think not just myself, but Dr. Radulescu, perhaps he can speak for himself, but where that slow combustion and that mixing come to become important. So what do you think about that?
Right. I just don't. Yeah, I think that is important, but like, because all this, like when we are actually doing an invisit simulations, all these things are all together, right? Like we don't know, like maybe they are equally important, or but I just think, like, if it's purely is only depending on this slow combustion, then by this relatively preliminary result I have, I was think like the implicit simulations gives the give the trend the other way, maybe over predicts the enhancing effect of instabilities than the experiments, right? Because like if your numerical simulations are solving a system that's that the numerical diffusivity is much greater than your physical diffusivity, you should see this numerical artifact helps this slow combustion to be more effective, right? So yeah, I don't have a clear answer, but and you say like the maybe the triple point, the pressure and temperature, it doesn't differ that much, but I think we need a more quantitative analysis, because at this higher temperatures, if you have a very unstable or very sensitive or very stiff reaction dependence on temperature, at the higher temperature this difference is more significant, right? Like maybe different by only like 10%, and it can give you orders of magnitude different reaction rate, and that can give you like stronger explosion kernels, and that may like make all the shock front dynamics different, right? So yeah, because I'm not sure saying for sure that what I'm trying to say here is correct, but I just think at least I'm not as sure as Professor Radulescu that only the slow combustion is the things we are failing to resolve from Euler equation simulations, right?
And I think Dr. Radulescu would like to say something.
So if you bring back your slide in the beginning of your presentation, in which you show one of the photographs that shows the structure of a detonation. Yeah, perhaps that one. Your slide 3. So if you want to ask yourself what happens to these pockets, you do the experiment, and then if you do a lot of experiments, then if you have the time resolution to monitor things, then you can see how things evolve dynamically.
Right.
And this is what we did. And if you look at those unreacted pockets, and you do your best experimentally to estimate what is the state of the gas inside of those pockets, and then you ask yourself, like, what's controlling that pocket burnout? Well, since you know the state, you can calculate some ignition delay, and that's going to give you a time scale for auto ignition, and you can also calculate some sort of time scale for flame propagation, and you can calculate what's the flame speed at those conditions. You can still ask those questions, and you'll find that the flame speed is tens of meters per second, and in fact, if you just assume that those things burn by laminar flames, they would burn on time scales that are similar to detonation, maybe off by a factor of 5 or so. And so if you have a turbulent flame or a wrinkle flame that has a burning velocity higher than the laminar one by a factor of 5, then you have your phenomena. And so to me, it's clear after looking at these experiments in a wide range of mixtures, in which we see these pockets burn out on on a time scale faster than 5 times that associated with the laminar flame, that these are just pockets burning out from their surface through diffusive phenomena. That doesn't say that the fast stuff is not important, and it's obviously equally important, because in your detonation, because it's unstable, it will generate these hotspots, these shock reflections that create stronger shocks, and that accelerate the reactions even faster. So that part is extremely important as well. You can't just say that it's a diffusive flame. You have these hotspot that ignites part of the gas, and then the other part of the gas is ignited by what you have ignited already. Having said that, I think there's something where we do have to focus. It's in a better reproduction of the coupling between gas dynamics and chemical reactions. In that all the observations that have been made so far are based on a one-step Arrhenius reaction or some modification to that kind of tries to reproduce the correct chemistry. But the correct chemistry is much stiffer than any of these one-step reactions that you have looked at or others have looked at. The timescales of energy deposition are orders of magnitude faster. And so those phenomena may be responsible for very rapid amplification of acoustic waves, much more so than what you would get in the one-step chemistry. And so there's the fast component is certainly very important, and there's a lot of work to be done into studying the coupling of gas dynamics with chemical reactions alone.
Yeah, I totally agree with that. I think like definitely I'm now saying like we should just like keep doing this this simplified chemistry forever. Just and I know like I can anticipate that if we put in all this realistic or detailed chemistry or appropriately reduced kinetics, then we should see like we will see like whether just the richer dynamics and perhaps more relevant to real detonations. But and also I'm aware of this experimental evidence that your group have been collected over the years, and I'm very sure about like that is that making sense, like this measurement of flame speed that this unburned pocket is burned out is way greater than what you can calculate based on assuming a laminar flame. But this somehow like what I'm baffled is not about that. I just think like if that's the case, if like the order equations are resolved at the level that the numerical diffusion is much greater than the realistic diffusion, why the unburned pocket in the inviscid simulations are not burned out faster than realistic?
Well, try doing your numerical calculation with 1 or 2 points per reaction zone. Then you'll see that everything burns extremely fast, and you'll recover the experiment. So your statement that the numerical diffusion doesn't reproduce it is that you don't have enough of it. So if you do a calculation with 1 point per reaction zone, then you're gonna get burning out extremely fast.
Yeah, but the things like for this actually for now, like I tried like the numerical resolution already high enough. Like I think, well, not enough, but much higher than 1 point per reaction zone length. I think that the result I show at the end for the Navier-Stokes equations is already like 128 cells per half reaction zone length, and still we don't see the strong effect of the physical diffusion that we put into the model. So I just don't know, like that means like even at that very high resolution, you are still having a more or a stronger diffusive phenomena than in the reality, and we are seeing the opposite trend for the dependence on EA. So I just don't know, like, but this is complex problem. I know it's related to all the other parameters. What happens if we have a realistic kinetics, or what happens if I have a like temperature dependent transport properties, all these things. I don't think it's an easy question, but I'm just not, perhaps not as sure as you are about like, you know, like why the implicit simulations are failing at, right? I just, yeah, anyway, just my, yeah.
Is that in your treatment, you assign the regularity of your detonation to a sole parameter, the activation energy,
right?
And you argue that I vary the activation energy and I get this, where whereas experiment shows that I'm going to get something else. That's not true. You have to look at what the experiment says. You have to look at the experiments. You have to look at what conditions they were done, what gases they were done, and then try and cook a model that reproduces those observations, reproduces what gas you're in, reproduces what conditions you're in, etc.
Right.
And so the regularity of your cellular detonation is not just controlled by the activation energy. In fact, there's no such experiment in which you can go to the lab and you can tune the activation energy knob.
Yeah.
There's no such thing.
Right.
There's every mixture has its own characteristics, and so you have to broaden up your little bit of your thinking, in that there's other parameters that vary from mixture to mixture that could also control their dynamics. And one extremely important one is the ratio of specific heats. It's the what happens to gamma. Now you've shown in your first part of your talk that gamma plays a huge role in controlling this super detonation. Well, gamma also plays a huge role in gas dynamics. It's the compressibility of the gas. If gamma approaches to 1, it means that you can squeeze that gas to like infinitely thin space. Okay, you can compress it to infinite density. And so that means that in your structure of your detonations, as you're going to a gamma that goes closer and closer and closer to 1, you're able to compress that material much more effectively, and that gives rise to like very complicated hydrodynamics that aren't at all considered in your discussion. So I think the part of the control of gamma on the hydrodynamics is extremely important as well. And in fact, we've shown in a few work, and Shem also has studied this for his thesis, that if you ask the question, can you correlate the cell regularity with gamma, then there's almost a perfect correlation in that irregular cells correspond to gamma that's low, and the regular cells correspond to a gamma that's high, and it has nothing to do with activation energy. And so you have to untangle these arguments. You can't just say one effect, and that's the effect that I'm going to study. You have to have an open mind and consider all the evidence that's available to you.
I totally agree. I agree. But I mean, this is, I just try to somewhat rationalize what we already have. But like I agree, like to consider this, we definitely like need to consider all these complexities and the full parametric space of the real mixture, right? Yeah, that makes sense. Thank you.
Thank you very much, Dr. Radulescu. Are there any other questions? I guess if you have any questions, thank you very much, XiaoCheng Mi, for your presentation. If there's any, I guess I'll introduce the next presentation, which will be or planned to be on December 7th by Dr. Wenhu Han.
Oh no, actually, sorry, Shem, I don't think Wenhu can make on the 7th. I think it's going to be Hongxia. I already asked Hongxia. I think she can present on the 7th, which is in
so we'll have Hongxia Yang next week, presenting on the dynamics of cellular flames with shockwaves. I assume we'll send you that email. And if there's unless there's any other questions or comments, I'd like to thank the speaker again, and thank you all for your comments and questions. And that's it.
Right. Thank you. Thank you for hosting.
Very good week.
Thank you. Yeah, you too. Thanks. Bye-bye.
Thanks.
Bye-bye. See you.